Okay, so welcome to another video on integration techniques. In this video, we're going to be looking at the integral of the form a to the power of x. Now, you might be familiar with the integral of e to the power of x. So essentially what you have in that case is you're going to have e to the power of x. It does not change, it stays the same, and then you just divide by the constant that is attached to x. So in this case it's 1, so we divide by 1, and then you get plus c. In this case though, it's a little bit it's not as obvious, I would say, because now you have a base that is different from e, so it does not retain the same kind of property. But there's a really nice trick that you can learn, and it is you can sort of guess what the answer is going to be if you take the function a to the power of x and you differentiate it. So suppose we take this function and we differentiate it. Now obviously if you're not familiar with the actual result for this, you wouldn't know what that is. So in this case, if we want to work the answer from first principles, what you can do is you can set this equal to some function y. So let y goes to a to the power of x. And now what we're going to do is we're going to take natural log of both sides. So this becomes natural log of y equals to natural log, so x times natural log of a. So now what you can do is you can differentiate both sides. So on this side you have y, which is a function of x. So you're going to have to use the chain rule to differentiate this. So essentially what you're going to have is the derivative of the outside function, which is natural log of y with respect to y, which is going to give you 1 over y. And now you're going to multiply that by the derivative of the function inside, which is y with respect to x. So that would be dy over dx. So this is going to be the derivative of this whole function. And now on this side, if you differentiate it with respect to x, this is going to become 1. And now you have this constant multiplying it, so you just have natural log of a. Now what you can do is you can say, okay, let's say I have dy over dx, and I make this equal to y times natural log of a. But this is not a function of x, which is what you wanted originally. So how about we just substitute that back in here, and this gives us a to the power of x times natural log of a. And this essentially works for any kind of number a. So you can just have the function remains the same, but you're going to multiply by the natural log of a. And how do you know this actually works? Well, if you use e as the base, let's say you differentiate e to the power of x using this formula. Well, you're going to have e to the power of x times natural log of e. And you know that the natural log of e by definition is just 1. So it becomes e to the power of x. So now that we have this handy formula, what you can do is, well, if you're integrating that function, then it makes sense that instead of multiplying it, you would have to divide it. So what we can say is a to the power of x dx integrated is going to be a to the power of x over natural log of a plus some constant c. And now you can check, because if you differentiate this whole function, you get a to the power of x times natural log of a. That's going to cancel out with this, and then you're going to get back to a to the power of x. Now we can make this a little bit more general, and we can say something like, let's integrate a to the power of beta x dx. Well, in that case, how would that actually compare? Well, if we perform the exact same kind of thing again, let some function y equals to a to the power of beta x, take natural log of both sides, that becomes ln y equals to beta x natural log of x, actually of a. Differentiate both sides with respect to x, then you get 1 over y dy over dx here. And then what you can do is, well, this is going to become beta natural log of a. And then doing the rearranging again, you get the derivative dy over dx equals to y times that, which is just going to be a beta x times beta natural log of a. So now if you're multiplying the same function by this, upon differentiation, you can guess that by integration, you're just going to have to divide by that. So you're going to have a to the power of beta x over beta natural log of a plus c. So let's put that into practice. Let's say I get the following function, 3 to the power of 2x dx. Well, we know that all we need to do is we're going to have the same function. It's not really going to change. But now we're going to multiply 2, which is the derivative of the top, by the natural log of the base, which is natural log of 3, plus some constant c of integration. Now, if we perform differentiation on this function, all we need to do is, well, we're going to use this formula. So we're going to have 2 times natural log of 3. That's going to be multiplied by this function. So that's going to cancel out with this. And we're back to 3 to the power of 2x. And the great thing about this is that it generally works for any kind of function that you have. So even if you had a negative power, like in the case a to the minus beta x dx, now that's not really going to change much because, you know, you're just going to multiply it by a minus 1. So you have a to the minus beta x over minus beta times natural log of a plus c. Just in the same way that when you integrate a function of e to the power of some minus power or some negative power, you're just going to have a negative answer. And that's in general just the essence of integrating functions that contain a power that is not really a function of e, but rather some other constant. It could be a fraction, it could be a decimal, it could be anything, because you're just taking the natural log of that to get the answer.